Dear students, today we will discuss about Poynting theorem. Basically, this theorem tells about the net outward power flow from a given volume. Any theorem has its own statement. Like that, Poynting theorem is also has its own statement. It is given by, statement is like this. It is given by net outward power flow, net outward, here P indicates the power flow, net out power flow from a given volume, is equal to, it is equivalent to, is equivalent to decrement of, decrement of rate of change of energy stored in electric and magnetic fields minus ohmic losses, okay, decrement of, here it is a DEC indicate decrement of energy stored in electric and magnetic fields, minus ohmic losses, minus ohmic losses. Mathematically, it can be written like this. That is, net outward power flow can be written like this. That is integral E cross H dot ds is equal to decrement. The decrement can be represented by minus integral 1 by 2 epsilon E square plus 1 by 2 mu H square dV, that is volume integral for these 1 by 2 epsilon E square and 1 by 2 mu H square minus ohmic losses. That ohmic power loss can be represented like this. That is integral sigma E square dV. So this is the statement of the Poynting theorem and Poynting theorem in equation form. We can prove this equation. By using Maxwell's equations. Now, here we know that from Ampere's law, modified Ampere's law, del cross H is equal to sigma into E plus epsilon dou E by dou T. This is the equation from the modified Ampere's law, one of the Maxwell's equation. But if you see the equation, Poynting theorem equation, here we got sigma into E square. In order to get this equation or proof of this equation, that Poynting theorem, okay, here we have sigma E. In order to get the sigma E square, we need to multiply with E on both sides. That is simple multiplication or dot product. That is E dot del cross H. Let us apply E dot on both sides. Here E dot into sigma E gives what? Sigma E square. Here E dot product is simple multiplication, that is epsilon dou E by simple product only, that is epsilon dou E by dou T. Now, actually it is not del cross E, it is del cross H. Sigma E square. Here E into epsilon dou E by dou T. And here E dot del cross H. Actually, we know that del dot of two vectors, let us say here vectors H and E are the vectors, E cross H is equivalent to H dot del cross E, minus E dot del cross H. So what we required here, actually E dot del cross H is required. So let us write expression for this one. Then you have E dot del cross H E dot del cross H, this one only. This E dot del cross H is equal to what? H dot del cross E, H dot del cross E minus del dot E cross H is equal to, actually this E dot del cross H is equivalent to what? Sigma into E square plus E into epsilon dou E by dou T. Dou E by dou T. Now let us substitute the other Maxwell's equations, or else we know about del cross E, that H dot del cross E, which is equivalent to minus mu into, I am writing that minus here, minus mu into dou H by dou T, dou H by dou T minus del dot E cross H, which is equivalent to sigma into E square E dot or E into epsilon dou E by dou T. Let us simplify this one. Here we have minus H dot mu dou H by dou T. Let us send this term to this side. Okay. We can have, that is minus, I'm writing here, on right hand side and left hand side, what you have? Minus del dot E cross H, and another term is what? Minus H dot. So I am sending that term to this side, then it becomes plus H dot mu into dou H by dou T. And already we have right hand side terms that are sigma into E square E dot or E into epsilon dou E by dou T. Okay. Now this one, I am writing this H dot mu dou H by dou T, or H into mu dou H by dou T like this. That is H into mu into dou H by dou T is equivalent to dou by dou T of half mu H square. If you differentiate this one, you will get what? Half, that is constant, mu constant, and H square, differentiation of H square is what? 2H. And we need to differentiate again this one with respect to what? That is equivalent to what? Actually of mu H square differentiation 2H. And we need to again differentiate H with respect to T, dou H by dou T. So here 2 cancel. Finally, we have what? Mu into H dou H by dou T. Similarly, we can write E into epsilon dou E by dou T, dou E by dou T is equivalent to dou by dou T of half epsilon E square. Half epsilon E square. Actually, this one is the energy density in the magnetic field. This one is the energy density in the electric field. So that's why, therefore, we can write now we can write minus del dot E cross H is equivalent to sigma into E square. I am writing this term first, and next remaining two terms are what? That H into mu dou H by dou T can be written as what? Dou by dou T of half into mu H square. And another term, that is E into epsilon dou E by dou T, can be written as what? Dou by dou T of half epsilon into E square. Finally, let us apply volume integral on both sides, or multiply with the minus sign on both sides. We can write here minus into minus becomes a plus, and apply volume integral on both sides. That is del dot integral E cross H volume integral, that is dV, and all these terms multiplied with minus of dou by dou T. I am writing this dou by dou T terms, dou by dou T of epsilon E square, that is rate of change of energy density, and next here of mu H square minus sigma into E square. And as you applied volume integral on both sides, so volume integral is applied to these terms also, that is dv. Here integral dv. Okay, by applying Stokes theorem to this LHS side, we will get, that is Stokes theorem is used to convert closed surface integral into volume integral. As you have volume integral, this one becomes what? Closed surface integral. And when you converted closed surface integral into volume integral by using divergence theorem, here you will get divergence. Here without divergence, E cross H dot ds minus dou by dou t of volume integral of 1 by 2 epsilon E square plus 1 by 2 mu H square dv minus integral sigma E square dv. If you see the terms, actually we have the terms here. I am writing the terms here only. So E cross H, E cross H. What about the units? This one is having volts per meter and this one is having amps per meter, and it is the vector product. This vector product is known as Poynting vector. So volts into amps gives what? Watts. Watts per meter square. That means this Poynting vector is also known as what? Power density. Power density. Surface integral of power density gives the power. That's why this term is what? Net outward power flow. So this one is what? Power flow. It indicates what? Power flow. And next, another term, that is 1 by 2 epsilon E square integral, or else 1 by 2 epsilon E square is the energy density in the electric field. 1 by 2 mu H square is what? Energy density in the magnetic field. If you apply integration, volume integral for this one, we will get what? Energy. And rate of change of energy gives what? Power only. So this one is also power. So that's why it is what? A rate of change of energy stored in electric field and energy stored in the magnetic field minus ohmic loss. So this one is also power. So actually it is what? Sigma into E, that is sigma is J into sigma into E is J into E. So this one is what? Amps per meter square, and this one is volts per meter. That is what? Power per unit volume. Power per unit volume, that is power density. As you have here volume, that volume gets cancelled, and it is also indicating what? Power. Actually this one is the dissipated power. This one is the dissipated power. Coming to the direction of the Poynting vector, this Poynting vector is what? E cross H. This Poynting vector is always proportional to the both E and H. Suppose E is traveling along AE, the direction of the electric field is represented by AE, unit vector, and direction of magnetic field is represented by AH, that is unit vector. Then the direction of Poynting vector is AK. Actually this one AE cross AH gives AK. Okay, in order to get the relation, we have to take like this, that is AEH. That means it is AK, AE, AH. This one cross this one, that is AK cross AE gives what? AK cross AE gives what? Direction of the magnetic field, that is AH. And similarly AE cross AH gives what? Another one, that is AE cross AH gives what? AE cross AH gives what? AE cross. And AH cross AK gives what? AH cross AK gives what? A. So this is about the Poynting theorem and Poynting vector. To see the derivation, we started with this one, that is actually it is a statement: net outward power flow from a given volume is equal to the decrement of energy stored in electric and magnetic fields minus ohmic losses. Mathematically we have like this. Next, we started our derivation with modified Ampere's law, that is del cross H equal to sigma into E plus epsilon dou E by dou T. Multiply with E dot on both sides in order to get sigma into E square term like this. So we got like this, and we know del dot E cross H equal to what? H dot del cross E minus E dot del cross H. On left hand side we have E dot del cross H. That E dot del cross H equal to what? This one only, H dot del cross E minus del dot E cross H. So finally, by simplifying this one, we will get Okay, here we got like this, that is h dot mu dou h by dou t, and this h into mu dou h by dou t, e into this one actually, this one is e, capital E. So this one is e, e into epsilon dou e by dou t, which is equivalent to dou by dou t of epsilon e square. And after simplification, we got this equation. That equation is nothing but the Poynting theorem. And we know E cross H is equal to what? Power density. That is also known as Poynting vector. The units of this one is what? Watts per meter square. And it indicates what? Rate of dou by dou t of minus dou by dou t of 1 by 2 epsilon a square. Integral 1 by 2 epsilon a square, 1 by 2 mu h square dv is nothing but what? Rate of change of energy. And this one indicates that ohmic power loss or power is dissipated here. Okay. So in this way, we have proven we have discussed the Poynting theorem, and we have proven the Poynting theorem equation also. Thank you.